Now that we've looked at a lot of ways in which we can find probability for data when it's discrete, let's look in some more detail into how we can find the probability of data that's continuous in nature. As we saw previously, when we're dealing with continuous data, we need to know about the type of distribution that that data gives us. In other words, we need to know the shape of the curve of the distribution. We're going to look at a little more closely, going back to the normal curve, and how we can find areas under that curve which coincide with the probability or the areas under that curve. So if you recall, when we talked about normal distribution, they take on many different shapes and forms. You can see them all here. These are all normal curves. Some are tall, some are short. It all depends on, first of all, what their mean is and what their standard deviation. They can take on many appearances, but one of the commonalities that they have is that they're symmetric and they're centered around their mean, which is at the center of the curve, and their standard deviation. Those completely determine how our curves look. So since we have so many different curves that all depend on what particular distribution we have according to the mean and the standard deviation, we need a curve that we can sort of relate all these curves to. And this curve that we relate all of these other curves to is called the standard normal curve. We use it as a standard because it never changes. All of these will change depending on the type of data we're dealing with, but the standard normal curve always stays the same. First of all, it's always symmetric and bell-shaped. Of course, that's not really different from the other ones. These are all symmetric and bell-shaped, even though they look a little bit different. But the one thing that does stay consistent with our curves is that the mean is always at 0 and the standard deviation will always be 1. This is very convenient for us because when we go one to the right and one to the left, we know we are actually looking at the first standard deviations, which mean, according to our empirical rule, that we've captured 68% of our data at about 1 standard deviation and about 95% of our data at 2 standard deviations, etc. And of course, the area under the standard normal curve, just like all the other curves, will equal 1. Keep in mind what that 1 means. That 1 represents 100% of our data. And of course, the x-axis is the horizontal asymptote. So not a whole lot of things there, but there's a formula that we use that helps us translate what our values would be on the curve that we have to what they would be on the standard normal curve. And this is called the z formula. This is called our z-score. And what it does is it helps us translate from one curve to another. For example, let's say we have a data value here. What that data value would be would depend on the distribution of my values. My mean would be something, and if I go a certain distance from that, I would have a value here. If I take this value and put it in for the x here, and then subtract the mean from it, divide by the standard deviation, I get a whole other value, and that value is where I would be on the standard normal curve. And so you want to think of the z formula as sort of a transformation value. It's taking it from our data and transforming it to what it would be under the standard normal curve. So for example, if we have a population that has a mean of 48 and a standard deviation of 5, if we want to know what the standard normal curve value would be, or the z value would be, when x is equal to 45, we can take a look at both distributions. 45, of course, if we drew out going 5 to the left, 3 times in each direction, 45 we can see is somewhere between 0, or the mean, and our first standard deviation to the left. Not quite all the way there, somewhere in between. So we know on the standard normal curve, it should fall also somewhere between 0 and -1. We can find out exactly where it is by plugging it in for x, subtracting the mean, and dividing by the standard deviation. This gives us negative 3/5, which translates into about negative 0.6 or 6/10. And so that is the z-value of 45. In fact, this, if you remember that the standard deviation is always at 1 and negative 1 on the standard normal curve, we can actually interpret this 0.6 as meaning we are 0.6 or 3/5 of the way to negative 1 standard deviations away from the mean, which makes sense. We can see we're not exactly one standard deviation of the way, we're a little less than one standard deviation, and we're to the left. Because we're to the left of 0, that negative tells me we're on the left-hand side there. But the individual z-values are not usually the most important part of our standard normal curve. The point of a z-score is that it can tell us how extreme our data value is. A really large z-score on the left or the right means that we are really atypical from most of the data. It means we're really on the extreme ends in either end of the curve. So it does tell us how extreme an individual data value is, but it doesn't tell us much beyond that. What's really important is the area of the curve. The area is telling me what percent of my data lies between certain boundaries. So it's giving us a percentage of the population that will fall within a given range. Again, here's kind of a picture of what we're talking about. I have a boundary on the left of A, a boundary on the right of B, and I would like to know what percent of my data falls between A and B. Well, once I can translate this over to z-values, we can find that area. Now, it's really important at this point. You have the z-chart that is posted, and you printed that out so you can reference that as we go on to the next slides. Let me explain a little bit about the problem that we have in finding this area. The biggest problem is that this is a curved line. And so in order to find the area between A and B, we would actually have to use calculus. And we would need to know the equation of this particular line that's curving here. And we could do that. We could find an equation that would describe that particular curve. And then, once we have that equation, as long as we understand calculus, we could find the area between A and B using calculus. However, most of you may have not taken calculus, and so we need an alternative way to do that. One of the ways we do that is with our z-table, and we're going to take a look at that. What we're going to do is we're going to again translate what A is and what B is on standard normal curve. In other words, we're going to find their z-scores, and then we're going to use this table to find their areas. So for example, let's say we wanted to find the area of the graph to the left of 1.75. Actually, there's a typo there. That should be negative 1.75, and you'll see that here on my chart. So negative 1.75, I want to know what the area is to the left of that, so I want to know the area over here. So if you grab your z-table, you can see that on your table, I believe it's on the left-hand side. Some tables have them on the left, some have them on the right. But on the column on the right or the left, you should see Z at the top and then a bunch of numbers falling below it. These numbers will represent the first one's value and the 10th value of the z-score you're after. So in this case, since we want negative 1.75, I'm going to go down to negative 1.7. And then because I also have a 5 here in the hundreds place, this is where we go across the top here. The top numbers tell you, the hundreds place of your z-score. So we have a negative 1.7 and then 5 in the hundred spot. So we find the intersection of that row and that column. And you can see that this right here is the area to its left. In fact, your z-table will always give you area to the left of whatever z-score you look up. So the body contains the areas to the left, and the top row and the side column give you your z-values. These only go to the 10th spot, and then your 100th spot is located up here. And it's about finding the intersection of those two places. So what is the area to the left of positive 1.75? So now if we go to the positive column on your chart, see if you can find, so you're going to flip it over if you have the printout that I have there, or go to the second page. Find that and figure out if you can find the area to the left of positive 1.75. What you should see is 0.9599, basically, and or 0.9589, something to that effect. That rounds, of course, to 0.96, so I put 0.96 here. What about the area to the left of 1.23? If you look that up, what you should see is 0.8907. Now we're going to go and talk about the right. We found the left of positive 1.75. What would be the area to its right? Now this is tricky because our chart only gives us areas to the left. However, because we know that the total area of the curve is 1, if I take the area that I found up here and subtract it from 1, I actually find the area to its right, which of course you'll notice the area to its right is equal to what the area to the left was of negative 1.75. That's because the curve is symmetric. So if you have the same number but different signs, you're going to be finding similar areas. So to the area to the right of 1.23, we know we're going to take the complement of this. This was the area to its left. So therefore the area to its right is going to be 1 minus that area, 0.1093. Another alternative would be to look up negative 1.23. If you look up negative 1.23 on your chart, you're going to see the same area there, 0.1093. That's because, again, the z-curve is symmetric. Now that we've looked how to do it with the z-table, and I do want you to be somewhat familiar with that. It can be a really handy thing, and we will use it from time to time. But let's look at how we're going to use technology to find area. It's definitely a lot easier, and in some circumstances, and it is the main way we are going to be finding areas on its z-curve in this class. So on your calculator, what you want to find is second, and then VARS, V-A-R-S. It is located right under the arrow keys on your calculator if you have a TI-83 or 84. So when you go second VARS, which really is taking you to the distribution list, go to choice number 2, normal CDF. You can either hit 2 or highlight normal CDF number 2 and hit enter. There's 4 pieces of data that you're going to need to enter into your calculator once you've hit that. Either it'll take you to a different screen where it has 4 different categories for you to fill in, or it's just going to write normal CDF with an open parenthesis. We need to put in the lower boundary of the area we're after, the upper boundary of the area we're after, meaning the right-hand boundary and the left-hand boundary for lower. So you can think lower is left, upper is right. And then we want to put what the mean of the distribution is and the standard deviation of our distribution. Let me say one more thing about this. For a standard normal curve, the mean is always 0 and the standard deviation is 1. So if the lower and the upper boundaries that we're going to be entering are z-values, which we'll start off with that, then the mean and the standard deviation are just going to be 0, and 1. Let's also look at an example. What is the area to the left of z equal to 1.45? Here's a picture of the standard normal curve. 1.45 is just a little bit halfway, a little less than halfway between 1 and 2. Now, in putting in a lower and an upper boundary, the problem that we run into is that if we're just going to the left of negative 1.45, our z curve, hypothetically, or I shouldn't say hypothetically, but theoretically, goes on for infinity. And so we don't have any real boundary that's on the left-hand side. We do have an upper boundary for this area we're after. Picture we're finding this area that I'm kind of moving my cursor around it. So the left-hand boundary becomes a problem because we do not have a button for infinity. The solution that we do is just put an extreme enough negative or positive number. If we've got a positive boundary up here. On the left, it's going to be a negative number. You can see that's the trend of our numbers. They're going negative. So we just need to pick something that's extreme enough. Remember, once you get past negative 3, we've captured almost 99.7% of my data. So any distance we go beyond that, beyond negative 3, it's already pretty extreme. So if we put something really big, like say negative 1,000, that will suffice. That will act as a negative infinity for our purposes. Some of your calculators may already enter negative 1 E99, which also acts as kind of a negative infinity. It's a negative 1 with 99 zeros after it. But we don't even have to get that extreme. So here's what we put into our calculators. Normal CDF, negative 1,000. As you're entering the negative, make sure you use the negative that's below 3 on your calculator, not the subtraction symbol. So picture it like a box. We're trying to box in the area that we're after. The left-hand side of my box is at negative 1,000. The right-hand side of my box is at 1.45. And then we have 0 for our mean and 1 for our standard deviation because these are z values that we're entering. The area we get is 0.9265. In other words, 92.65% of my data is between negative 1,000 and positive 1.45. What's the area to the right then of negative 2.153? I'm just picking these z values at random, something for us to use. So here we go, we're a little bit further to the left now. Excuse me. And we don't have an upper boundary. So we run into that same problem. We don't have a number for up here. So I'm going to choose something that's extreme enough to the right, like positive 1,000. So negative 2.153, 1,000, comma 0, comma 1. Make sure you're putting commas in between these as well. There's a comma button right above your 7. And our mean and our standard deviation are 0 and 1. Here you should get 0.9840, meaning 98.4% of my data is between negative 2.143 and positive 1,000. What is the area between negative 2.153 and positive 1.45? So now we actually have two boundaries, solid boundaries, that I'm working within. So I don't have to worry about that whole extreme value on the left or the right. We have two solid boundaries. So my lower boundary, again, my left-hand boundary is this number. Right-hand boundary, 1.45, comma 0, comma 1. And you should get 0.9108. And I have the wrong thing here. This should say 0.9108. So now, on your own, I would like you to find the area between negative 2.18 and 1.44. If you're working this on your calculator, you probably calculated the answer. I want to explore a little bit about what this means in terms of probability. Since the curve itself is representing my sample space, meaning all possible outcomes, The shaded area actually represents successful outcomes. So therefore, what we can do, remember successful outcomes divided by the sample space is measured as a probability. So the probability that my value x is going to fall between negative 2.18 and positive 1.44 is 91.05%, or 0.9105. So this is how we can think of this in terms of probability. We're thinking of it in terms of probability of picking a random value that will fall between these boundaries. So, putting this into probability notation, let's find the probability that a random score would fall as follows. The probability that a randomly picked z-score would be less than 1.43. See if you can figure out what that would be in terms of your z-value, and the probability would be less than 1.43. Use your normal CDF on your calculators. Pause if needed. The probability that z would be less than 1.43 is 0.9236. Also, the probability that your z-value would be greater than negative 0.81. Again, using normal CDF on your calculators, see if you can figure out the area, hence the probability that z would be greater than negative 0.81. Pause if needed. The answer is 0.7910. And then here's our last one. Find the probability that a randomly picked z-score would fall between negative 2.81 and 1.14. Pause if needed. The answer is 0.1246. So there's a 12.46 probability that it would land between these numbers. Remember that your probability P must always be between 0 and 1. Just as we would never have a negative area, we would also never have a negative probability. One of the things that can happen, for example, if you put negative 1.14 as your lower boundary and negative 2.81 as your upper boundary, is this would come out as a negative answer, just because you would reverse the lower and the upper boundary. So be aware of that. Probability should never be less than a 1.